Hello, everyone. I'm Xiong. I'm very glad to get the invite to present this multimodal agent areas. I saw you already listened the exact same area, the multimodal agent last week. Hopefully, I would bring something new in this direction. So first, I want to show this plot to everyone. So how you can see how crazy it is, right? In the past 5 years, almost all the benchmarks get saturated. And now we have the last one, which is the one that proposed this year, the humans last exam. Seems like when we solve this one, we solved AGI. I'm not sure whether we can solve it this year, but I believe we'll have a much better result for this data set, these benchmarks by end of this year. Okay, since we have so powerful frontier foundation models, then what we should do on those models, how we could leverage them to make our world, make the society better? I think the answer is agent. We believe the multimodal AI agent is the next generation of applications. Why? It's because we want agent is not just reading text. We want the agent can hear, can see, can speak, can feel even. And we want agents that to process a task like a human. That because most of the tasks that when we do in computer, they involve multiple apps interfaces. So powered with the new advanced the language model or the large foundation model, which is vision, language, action models, it could make the digital interactions more acceptable, more automated, and increase the human's productivity. So, okay, so what is the status of the multimodal agent now? How far it is? Actually, it's not far away. We already see a lot of the multimodal agents be used in the real world, or some of them is used in real world, I would say. Some of them still in the research. Like for example, the coding agents. I think some of you, maybe a lot of you, are using the coding assistant or agent products like the Cursor, Replit, or Devin in your daily work or research. And those agents is not only that can accept the code text, they also can let you to upload the images, and they could to generate the code or fix your bug through the images you send. Web agents. The web agents is also a multimodal agent that the agent could could automate some control in your browser or apps, same as the mobile agents and the even physical agent. Super amazing, right? So this is a robot called Helix from Figure AI. It's not just show you interact with a single robot. Even they could let robot and robot collaborate together through the powerful these foundation models. So all those agents, some of them in production, some of them is still in research, some of them is a demo stage. And I believe we are going to have more and more this type of applied use cases of multimodal agents. So the question is, how are we going to develop them? And what is the challenge for developing those multimodal agents? And what is the important component, what we should focus on? So this is today's agenda. I will talk about the multimodal agents from these 3 areas. First is environment benchmark. We need an interactive environment. We need this environment can be more reconfigurable, expandable, not just static benchmarks for multimodal agents. We need data. How we get data to train our multimodal agents. The third one is what's the model we should build on. We interact with computers every day and use that to perform a lot of different tasks, including like web browsing, editing some personal videos, managing our files, doing some analyze, or doing coding to implement some softwares. And for those tasks, they are not just it's not just for those tasks. It's not just interact with a single app. It is a workflow that will involve multiple applications through GUI or CLI. And with multimodal agents, it have a big potential that can help us to revolutionize this interaction between us and this computer environment. The agents can follow our high-level natural language instruction and to automatically to do those interactions. For example, in this image, in this slide, there's a task called update the bookkeeping sheet with my recent transactions over the past few days in the provided folder. It is a very boring task. For this type of task, I think everyone would like to have an agent to help them process those tasks if there isn't one. However, to build those agents, you need, how can you trust those agents? We need to have a benchmark. So currently, there is a major challenge in developing those multimodal agents. That we don't have a benchmark that is depends on the real interactive environment. That this environment can cover the more diverse and the complex real world the computer use the scenarios, and also can support the different operating system interfaces, apps. So with this type of benchmark, after the agent pass that benchmark, we can trust this agent for our daily use. So currently, they already have some good benchmarks, but they are not have these properties I just mentioned, like the MOOC. So MOOC is a real good benchmark. They include a lot of good the real testing. However, for each the test in the MOOC, it has only single demonstrations without the executable environment. So the assumption from the MOOC is for each task, there is only single solution, which is not true 100%. And with that benchmark, it would would paralyze some alternative correct solutions. The web arena is another good benchmark. It is an executable environment. However, it simplified the observations and action space that it only covers very limited the task and the applications or domains. Like it only covers the web navigations on a few websites, domains. So in that one, it restricts the testing in the use cases for the agents. And also it cannot use to evaluate some open man tasks in the complex real world scenarios. That maybe they require some tasks require the navigating between the multiple different applications and interfaces in the open domain. To address this gap between the development, the real world use case and the model development, the model development, the simulation environment. So we introduced the OSWorld. This is the first, the scalable and the real computer environment for development and the benchmarking of multimodal agents. Why it is, I would say, it is a real computer environment. It's and it could be used for the both development and the benchmarking of the multimodal agents. Because the OSWorld first, this environment allows the freeform, the keyboard mouse control of the real computer applications. And it's not the fixed the evaluation set. You could to configure your tasks and execute those tasks through this through this interactive way. Through this one, then you can use the OSWorld to evaluate some open-ended computer tasks and with the arbitrary applications. So it's not fixed. Maybe you can do ranging from different use case like a software development use case or the image editing use case. The OSWorld can serve as a unified real-world, real computer environment that allows the users. So in this way, they can allow users to define the agent task, define a new agent task without to build this new domain-specific simulation environment. So it's as an environment. So OSWorld is more flexible and give the users more control for the environment design for the scenarios they care. So let's see how we're going to use the OSWorld to create the different tasks. So first, for each task, you have a natural language task instruction for the task. So you see here, you have a task. You want to create this testing environment, like updating. This one is, I just mentioned this task, updating this bookkeep sheet. And with this instruction, in the OSWorld, they provide the initial state setup for this instruction. So the setup is it's a file. You just need to create this file. In this file, they include multiple components. The right part is you need to configure the initial tasks, like this Excel files means the tasks. And also you need to add what is your post-processing and those configurations. And also where you can to retrieve the files and the information in the yellow part. And the last one is how you're going to evaluate after you finish the task in the environment. After you configure your initial state, the setup, the OSWorld will initialize this environment with a virtual machine. And in the virtual machine, they will initialize. So the initialization will start to run in this virtual machine, and you get the initial states of the test environment. So it's very convenient. So for example, at this moment, you could use this virtual machine to restore
the task again and again, just to reuse this virtual machine. And because of we use this virtual machine, so it's a safe, isolated environment. So you don't need to worry about some damage in irreversible damages when you do testing. So when the task environment gets set up, then you can start to run your agent to interact with this environment. For example, you can use Sp25 to create an agent and interact with this environment. Or you can use any other open source model to build an agent. The agent will receive or observe different the information that can be provided by the environment. First, of course, is the user query, the natural language instruction from user. And also, it can to receive the observations from the environment, such as the screenshot, the accessibility tree, and some customized streams, maybe the terminal outputs. So here is an example, like the left side is it's called a set of mask, which is a screenshot plus some plus the information you extract from accessibility tree that you can add those the label like in the image, so it make they can provide more information or just screenshot. And also the right side is the dormitory. It's accessibility tree, but for left side is a dormitory. So after the agent receives those observations, of course, it's not say like every agent needs all the observations. It depends on your agent. If you are vision-based agent, maybe only use the screenshot or SOM. If it is a text-based agent, maybe you are only use accessibility tree. It depends on what agent you're going to build to interact with the environment. So after you receive those observations, the agent will it depends on how you create agent, but the agent finally will generate some executable actions, like you will click some position, or you will drag some content, drag some box, and etc. Through manipulate the keyboard and the mouse, and then each of those actions will be represented using it's a code string to generate it by the agent, and then the environment, the simulator will execute the code strings in the virtual machine, and you will get the new observations now. The OSWorld, we are using the Pi Auto GUI 3 to control the mouse and the keyboard. This will be used the library. So between this interaction loop will continue based on your instruction. It will repeat multiple steps until it terminated. Maybe it's done or fail, or it's reached the max number of steps you set. In our experiment, we said it's the 15 and 50. So after so now you can from you set up the task until you run your task, and then after task you stop, you get a result, then you will do evaluation on your task in this environment in OSWorld. In OSWorld, it's different from other benchmarks. We implement this execution-based the reward function. So when the final step reach the goal, of course, they'll get a positive reward, or even if partially achieved, they'll get some number between 0 and 1. If not, if totally failed, it will get 0. To get this reward, we are not just use the single the evaluation metric. Here is to evaluate this the successful execution of those tasks. We thinking there is no single way to evaluate the successful or fail for the task. So we make this evaluation more open. So what is open? So open means that you can construct the evaluation script by yourself in OSWorld development. Because some tasks you need to retrieval, some tasks you need to matching to evaluate your task. So we use this example-wise evaluation to design the evaluation metric for the tasks. So not just the fixed one. So it's an open one that you can base on different tasks to design your different evaluation metrics. So that you can facilitate the diversity of the tasks and could make the evaluation more reliable, especially for this complex real-world open-ended tasks. So we create this powerful OSWorld environment so that the people can use this environment to benchmarking their multimodal agents. Besides we build this development, of course, we also build a benchmark on top of the OSWorld. Here we introduce the 369 real-world computer tasks that involve widely used the web or desktop apps like its Office, OS, and daily use workflow and the professionals. All of them, each task is we did a lot of research in the internet. So all of them is based on the real world, the computer use cases, the experience. And we ask the people who had the CS background to interact with the initial stated, the initialized development in OSWorld, and interact with the development and record those the trajectories, and also handcrafted the a lot of the execution evaluation script, the evaluation scripts, execution-based evaluation scripts to verify the task completion. So in the left side, you can see the distribution of the different tasks. So total they have 369, and 100 is a workflow task, which is a multi-app. Means this task need to jump across different apps, multiple apps. And they have the 268, which is roughly 70% is a single app. And in those tasks, some of them, which is roughly 20%, is through the other data set like Web Arena. And there's a special here is we also add the 30 tasks which is infeasible, because you need to also know, agents should also know how to say no to the user. So we think adding the infeasible task is important to make it more comprehensive for the scenarios testing. And we also have a small number of 43 tasks for Windows, not just on Ubuntu. And as I said, because we thinking this example-based the evaluation script, I mean, it's very important for the real-world evaluation on multimodal agents.
we construct the 134 evaluation script on 369 samples. So you can see the ratio is very big. So here is some samples we sampled from our 300 the sets of in our benchmark. So you can see they cover very diverse the apps and across different the user intents. So we compared our benchmark with the current existing popular benchmarks from those different the perspectives, such as whether it provides the controllable executable environment, or whether it's easy to scale to the new environment, or it can support the multimodal, or whether it could be do the cross app the tasks, or whether it could the start task from the intermediate, the initial state, and so on. So we can see that our benchmark is to have more powerful, we cover different the scenarios, the request as a benchmark for the multimodal agents. And in the right side, we also did some analysis how complicated the tasks in the OSWorld benchmark. We did some comparison with the web arena. So the green, the blue is web arena and the yellow is the OSWorld. The median completion time for web arena is roughly 30-40 seconds, and for in OSWorld, the median completion time is roughly 100, maybe 110 seconds. And they also have some significant the number of samples maybe need even more, even need 900 seconds or even more. So it means that the complexity of this benchmark is also higher than the existing benchmarks. After we create a benchmark, we test the benchmark with the state-of-art, the LLM or VLM from the open source and also cross-source the foundation models like GPT-4, Gemini, Cloud, and etc. And the left side is the prompt we used. We designed the 4 different testing the settings through based on different observation. They are one is only have accessibility tree, which could be the LLM can directly to run it. And the second one is only screenshot, which is pure vision. And the third one is a screenshot plus accessibility tree. And the fourth one is set of marks. We did some some simplification on accessibility tree, because usually accessibility tree is very long and include a lot of the redundant information. So we did some simplification to reduce them to short the length of this text representation. So this is the results, the numbers we get. Let's do some analysis on this table. So first, let's see at the bottom of this table is a human performance, roughly 70 to 75% success rate. And if you go to see the performance of those the state-of-art open source and the frontier closed source model, it's still far behind, far from the real human performance on those daily use task. It's not like a super hard task. It's a daily use task. And second, you see like from different the scenarios, human performance is kind of stable. It's plus minus 3 to 5%. But for the those frontier models, those large foundation models, the performance change dramatically. And even the model from same company, like you see the, for example, in the set of MOOC, the GPT-4V and GPT-4o, the performance gap is huge, right? It's 10% gap, even the performance, since the performance only just 20%, they have 10% gap. And of course, so this is table is results is we get last year, and this year they have new models from the from those LLM vendors, the OpenAI and the Anthropic. They have some big improvement on there, but still it's far away from the human performance. We'll see. We did some analysis on what factors will influence the performance. So first, we did some analysis on the screenshot resolution. So we found, so first so 1 point, so in the y-axis is a successful rate, and the x-axis is a downsampling rate. So because of VLM most of VLM is still trying to very small resolution, not very small, but it's comparing with now we have better resolution, but usually the VLM not trained at the full resolution, is trained on some a smaller one. So we do some downsampling on the resolution, and then we calculate, then we run evaluation. In the GPT-4V screenshot, as you improve the screenshot, it get a better performance. But in the SOM, I think the trend still is improved, but still have this is a noise here. But still improve, but not as much as not as clear as the screenshot. I think it's because SOM also include some they have some extra information it gets from the accessibility tree based on, so they have some text information inside, so it decreases the impact of the resolution. And then we also doing some analysis on the how much the history context will influence the final performance. So we did this. We choose different number of the trajectory length. We found in the GPT-4V SOM, it improved as you add more and more the historical the information, the steps. But in the screenshot one, it doesn't. It even make it. It's even worse. We think it's mainly because the SOM have, like I said, it include the information from the text representation and accessibility tree, and our LLM is perform. It's the current foundation model is perform better on the text rather than the pure vision image. So I think we think that is the reason it's getting better and better with more and more context. But for the screenshot, it's getting worse. I think it's because the current the foundation model it's not be well trained for the computer use these scenarios. So it means we need to improve. It still have a gap, like the open source community or the closed source companies need to improve those the vision capabilities in the foundation model if we want to get better the multimodal agent for computer use. And in the right side, it's a length distribution of the accessibility tree. So although you can add more and more those text representation in the multimodal agent, and it can get better performance, but there have the issue there is the accessibility tree is super long. So roughly it's at the 90% percentile, it's 6K. So if we want to add more the history, the context, then we need to find a way to get a more simplified, or we should call it more concise accessibility tree. So maybe they have some work on how to select the relevant information in the accessibility tree before you fit into the system. But when you do this step, maybe your system will be slow because you need to do this information to maybe you need to train another big model to do this information processing on that add the extra the latency there. And we also analyzed the model performance on the Ubuntu and the Windows. We found that their correlation is pretty high, it's 0.7. And so which means like we could use the OSWorld framework, it would be effective. You could to get if you can test your model in one scenario, it should be it should be effectively transferred to another environment. And we also did some operation, like when we change the position size of the windows in the different app windows in the screen, the results also show very different. So which means it still means like the model is not those foundation model is not very robust to for this type of disturbance. So through this we can find they have a lot of work we need to improve, right? And the good news is recently they have a lot of the new progress in these areas. Anthropic, they have this new cloud 3.5 and also the 3.7, and we can see the very significant improvement from here 15% to 22%, but still far away from a human 72%. Of course, if you increase the number of steps from 15 to 50, it's getting better, but still have a big gap. And OpenAI also have this new model called operator, the CUD. And in their recent performance, CUA, sorry, in the recent performance, we can see OpenAI is significantly better than the Cloud 3.5. And at the 200 steps, they can get even like 38%, comparing with like maybe only have 15% 4 months ago. So it's improved super fast. But this is like you have 200 steps, but most of tasks in the OSWorld is roughly it should be most of it can be solved on the 15 or even 20 steps. So which means they still have a big improvement. They have big space to improve the multimodal agent for this computer use. Okay, so this is through the environment and the benchmark discussion. You know, we have made a lot of great progress on this computer use areas for multimodal agent, but still they have a lot of the stuff we need to improve. They still have a lot of opportunities there. Now after this, let's go to the data part, since we still need the data to train our model. For the agent training, I think we have a bigger challenge than we do in the LLM training. Why? Because the agent model is not a single step, it's a multi-step, it's a trajectory. Collecting the trajectory data is super expensive. And the second is, it's very hard to directly to get the trajectory data by crawl the internet. And second, even you say you have enough money, I can just to hire people to collect data. But to do those annotations, to collect the trajectory data, it's very time consuming. And it limits the scalability. Not good for the scaling law. The cost and the time consuming of the data collection through human, and also there's no free large scale trajectory corpus you can crawl, then what should we do? Okay, why don't we let the model to synthesize? So here I want to discuss this paper called the AgentTrek, so which is to synthesize the agent trajectories through this guiding plane way, the strategy with a web tutorial. So what does it mean? So first, we know they have a lot of a large collection of the tutorial-like text in the internet, right? And those text they provide the step-by-step guidance on how to perform different tasks. So we read it, we read those tutorials, and then how to interact with different apps and complete different tasks in our GUI environments. And then those tutorials, they cover different the scenarios. So we could to systematically to filtering those instruction contents from the internet. And of course, those data is not that clean because it's written for humans. So they have a lot of noise, text, descriptions, and of course, HTML formats there. So we need to extract the valuable the knowledges that knowledge the steps from those tutorial-like text, and then transform those unstructured text into a structured the agent trajectories with the definition or high-level description of the task that make it to allow the agent to use to train and mimic the human task completion. So in the AgentTrek, there have the 3 stages to do this. The first stage is called automatic tutorial collection from the internet. So in this step, as I just roughly described, we extract and filter those tutorial data from the internet using a bunch of heuristic the filtering and some classifier like with the fast text, and then transform it into some structured the format with using LLM. And the step 2 is the guided replay for those trajectory generation, which is using VLM, vision language model agent, to execute those tutorials based on this structured tutorial, the structured steps, and run it step by step. And through that, we will to collect the high-level trajectories, including the high-level description of the task, the observation of each step, and and the reasoning of each step and the final actions. And then given those data, we will run a separate evaluator to evaluate to assess the quality of the trajectory, to ensure to filter out some bad trajectories or low quality ones, to make sure to ensure the effectiveness of this data for the training. And the step 3 is we need to verify those agents by training a model and fine tune for the agent models to demonstrate the improvements and the significant performance improvement across different benchmarks. So that is roughly the steps for 3 stages for the AgentTrek. So like I described these 3 steps, let's go a little bit deeper about each step. The first step is this tutorial collection from the internet. So we start from some the big large corpus like Red Pajama, DCLM. Then we did the using maybe some filtering based on keywords or some structure features. And we did, after this step, we filter maybe 99% of data. And then for the remaining data, we extract the subset of the remaining data, the filter data, and use the LLM to did some annotation. It is a good data or is a bad data for the as a tutorial. And then after this annotation, we trained a fast text classifier and use that one to classify all the whole the filter data. And with then when you get this the tutorial data, we run another round of LLM to paraphrase those data to follow some predefined the format that used for the guided replay for the stage 2. So this is the data flow, the flow for the step 1 when you do the pre-filtering. So you can see we use some the heuristic filters to do the first step, the data filtering, and you can see like just after this 1, 2, 3, the 6th step, you could it will filter out more than 99.9% data. And after you get this filtered data, we select some status. We select a small number of the data and use the prompt LLM to classify is a GUI tutorial or not. So this is the prompt we use. After we do that, we also have the human to do some to sample some of them to verify. We find that F1 score is pretty high. It's like they can get roughly 88, 89%. And we find for some long text, very long text, the documents, the LLM is performed better than the human when they embed the tutorial in the long context, which is normal, which is not surprise, but so in this way we more trust the LLM on the long context classification than human. Then after we filtered those tutorial data, then we formalize the tutorial data into a specific the structured format that we want to use for the model for the replay, the guided replay. Here we organize. So the left side is the prompt we used, the goal. So we want through this prompt, we want to convert the tutorial into five parts. First is the platform and the target development that specify what is operating system, what software versions. So that will be used for the initial state. And second one is the task description, which to provide concise problem statements, which is the instruction. The third one is the prerequisites, which requires the dependencies, background knowledges, and fourth one is this step-by-step the instructions, which include this reasoning guidance and the command syntax. And the last one is the expected outcome, which is used for the verification or success indicators. So after we get this, after we paraphrase the tutorial, then we get this structured tutorial, and then we create a VLM agent and fit into this step-by-step tutorial, and the agent will start to run the interactor with the environment step-by-step through this observation action loop. And through this, after the whole execution, we will record it, all the observation, action, intermediate reasoning, the whole trajectories. And then those will fit into another VLM evaluator to assess the quality or correctness of the trajectory and ensure we got high quality data. So here is an example of in our the finalized data, the final version of the data after you doing all those steps. So you could see the left side is the observation sequence, and right side including the action, the source for each step, and the actions, the action code for each step. So comparing the data we collect using the AgentTrek with the prior works, the other data set people use to train model. First, our data could be through AgentTrek, you can collect much more data. Here we show this 10K. 10K is not the maximum. We just do some of them. It could be much bigger. And the second, the complexity of the data is not low. Actually, it's pretty good. Every step is 12 steps. And you also will have a lot of the information. You will have HTML, you will have accessibility, you also will have reasoning, you could get videos, you can get screenshots, and you can cover different websites. So the AgentTrek, it maintains the diversity and the realism because it's from real world. And it's also addressing the scalability issues that the human annotated data may have given the budget. So here is the distribution of the trajectories from the so this is the distribution. The left side is the distribution, the data the different number of trajectories from different websites. And the right side is from the high level, different the vertical, different domain, what's the distribution in the data. So you can see how the coverage of the data set, the domains through in the AgentTrek, I mean, to say like the data set created by the AgentTrek. So we did some like we said, we fine-tune the model to track the performance, to see how good this synthesized data comparing with other human annotated data in the benchmarks to train the agent in the benchmarks. So we did it on this comparison on the Web Arena dataset, the benchmark. Yeah. And the models trained on AgentTrek data significantly outperform both I think open source and even closed source GPT-4o models. So which demonstrate the just synthesized trajectories also it's also high quality, and it also can use to train a better model. This is about how we use the AgentTrek to do the data synthesis for the GUI agent. I think the takeaway from this AgentTrek work is leveraging the internet corpus is still an important way because they have diverse task resources. And second is with the reasoning and the reflection. Reasoning and reflection is very important. The factor for the trajectory, which we will talk about in the model side later. Yeah, but however, it still have an issue here is because for each instruction, you still only get a single trajectory, so which is an issue that not like you only have a single solution for each for the query. It could have multiple instructions. So we still have this issue here because it's only an imitation learning process. But I think we have the solution for it. It's OSWorld. So you can use AgentTrek to create the data for SFT training, and then you can use that high level instruction and run it in the OSWorld for the second stage, the IO training, and then you can solve this exploration process. Great. So we try to answer the question like we can use the data synthesis to make the existing real vision language model perform better on the GUI agent tasks. Then so the next I want to discuss is when you do data synthesis to improve this action call capability for agent for external tasks. How about it could also help for your internal the task itself, like understanding. We know like the vision language model is trained for the understanding. And if we want to do it, can we crawl from website? If the website have this type of data? I think the answer is not really. Then how can we synthesize? So first, let me see like why we need to do it. Why we want to synthesize this type of action data for multimodal LLM for understanding. Understanding should be the capability or skills it should have, right? But actually, it's not perfect, or it's far from perfect on the open source model. So here is the 4 examples from the 4 different perspectives to explain why we need the model to itself can do the action calling to improve the understanding. All those tasks, either they need more fine-grained the vision capability, or they need some reasoning capabilities, or they need some external knowledge. So here we introduce a tackle, which is through it synthesize this chain of thought and action data to improve the multimodal understanding capabilities through adding this action calling capabilities skills in the model. So this is some examples we showed after adding this action calling capability, which is trained through the synthetic data we will discuss later. It can generate the thoughts and the actions, and through the observations, they will do again until they get the results. So this is the one example, like to we just showed this failed in this Lava model. And this another one is called the localization and the functions, visual functions. And this is to query the external knowledge, the text knowledge, so not just the vision model only. And this makes the vision OCR and some calculate the capabilities. Okay, so let's go back, like how we create this the synthetic pipeline to synthesize, to generate this data for the COT training. There is a lot of details here, but don't worry, let's explain it one by one. It's not that complicated. So first, for this data synthesis pipeline, they have the 2 parts. First part is called the model-based generation, and the bottom part is the programmatic generation. So in the model-based generation, we take the existing image QA. We get those image and the QA pairs as input, and we prompt the model, the frontier models. I say like you have this image and the QA pair. Let's generate the chain of thought and action, given those the action or called action list, or chain of thought if they do not have the relevant action in the list. And then it will generate. And after it generate, either the chain of thought with action or chain of thought without action, then we will verify the outcome, the output. If it's correct, then we will pass it. If it's not, then we will convert this pair as the direct answer pair. So in this way, you will get the data. Not all of them have the action. Some of them have action. Some of them only have chain of thought. Some of them without this direct answer. So that is first this part, the top part, and in the bottom part, we do the programmatic generation. This way is we do not have the QA pairs in this programmatic generation process. So we only have the image. Then we use the model for maybe the detection model, depth model, OCR model, and different models, and also or could be human to label some data, some box. And we get those dense annotations in the image, and we designed some manually templates, and use that to generate the QA pairs. And through that one, we can to synthesize what actions in a formula answer to question to answer. So this is the template we use to do the programmatic generation. So some of them is about the counting, some of them is about the 2D spatial reasoning or 3D spatial reasoning. Some of them is the mixed understanding and the counting. Or so we try to mimic different the reasoning or the action call needed to answer different type of the questions. And then here the bottom is the action sets which cover like OCR, get object localization, depth estimation, crop, regular zoom in, zoom out, no zoom out, zoom in, and query language model, accurate soft math equation is pretty diverse. So through this two-way, we collect the data, and of course, in this data, we need to there have some of them is the chain of thought and action data, some of them is not. Then we need to do some analysis on those data and test on the benchmarks. So first one, through the experiment, first one we found to get the model, get the multimodal foundation models to have this reasoning or action call capabilities, you need to use fine tuning. In the results we found, it few shot or in context learning doesn't work. And the second is we found that they have comparing for the tasks with this action, adding this action capabilities. It's really to improve their capabilities to solve the task it cannot solve before, to improve their understanding capabilities. So which means that even the understanding this capabilities, it also could be enhanced by adding the external tools and make it through this function call or tool calling to improve it, which is not a surprise, but it's also interesting to see this positive results. So it can give us a different another direction how could we improving our models on understanding. And this is the second observation we found. The best COT data. So the COT data, the best one, which can almost it test on the different the scenarios that you see like it tests on this VQA, Blink, math with time MMU. It's almost improve all the tasks, which means like so adding this action capability in the model in the data set, to create this chain of thought action data, it can improve and with this data to train the model, the multimodal model, it can improve the model understanding capability in general, not like just improve one model, one bench. And the third observation from this the TACO experiments on the COT, the chain of thought action data set, we find that the quality is more important than quantity. Not just add more, you will get a better performance. Okay, so this paper is to talk about how we could add in the action call capability into the multimodal language model or foundation model, and first you need to fine tune a model, not through the few shot. And second is COT data is consistent to improve those the models through this fine tuning on this instruction, this synthesized data. And the fourth one is the quality is more important than quantity, which is not new, but it's some lessons we learned from here. So here is we have discussed about the environment benchmarking and the data synthesis. I think now you already have the comprehensive view, holistic view about these multi-agent areas. If you want to test the agent, if you want to generate the data, and if you want to do the IL in the environment, you already have those tools, and you can start to create your multimodal agent. So the last one, I want to spend some time talk about the model. Although I'm not saying like this is the best model, but I think you can learn from some insights from those models, I think. So right now, every day they have new models. So they always have a better one. So I hope like we can discuss some different things about the model here. So I want to discuss this paper is Argwis, our paper, which is a unified pure vision model for the GUI agent. For the GUI agents, we found that they have three not problems, three issues like we want to solve. First is most of GUI agents is text-based. Use a text representation like a accessibility tree. Second, the visual grounding performance capability is not good. I think it's because most of the model not really to train their model for the computer use. And third one is most of the model is to generate an action directly without reason. So here is some more concrete the slides about these three observations or issues. The first one you can see they have different the textual representation. Some like in the web is HTML, maybe DOM tree, and in the OS they have another type of accessibility tree, and the mobile have different ones. And most of all of them is super long, super lengthy, and it could be longer and longer as the complexity of your GUI. So comparing with the vision based, pure vision based, vision is just one. So whatever your background code looks like, the image is same. So that is one about the benefit of the GUI agent. The second one is because of different systems use different tools, the action space is very different. It's not a big issue, but it's still an issue that it will prevent this effective cross-development learning. And also that you cannot to leverage different data, the training data together, which not good for the scalability. Then it's this visual grounding capability. So here is we tested on the mobile, desktop, and the web scenarios. We found those closed sourcing model perform surprising bad, I will say. So it means like the model doesn't really to optimize for the computer use scenarios by then. This is GPT-4, GPT-4o. The new one operator or Cloud 3.5, 3.7 is much. And here is an example like the current existing methods. They trained the agent to generate the low-level actions directly
like the director the code rather than the sophisticated reasoning concept, reasoning the text, which would make to get those models or those agents very struggle on the complex scenarios in the real world. That may require more careful planning, which those planning knowledge could be transferred from the text text corpus which trained in the LLM. So given these three issues, we propose this algorithm model. First is the pure vision based. So it doesn't matter what its accessibility tree format is using in the system or in the web browser. And the second is we improve the grounding model through combine. We defined a new unified format to combine all the existing data and train the model to improve the grounding. And third one is we explicitly to include this reasoning process, what we call the inner monologue, into our training, the model training for the action generation. As I said, for the algorithms, we eliminate these dependencies on the platform-specific textual representation because it is pure vision based. It directly operates on the screen images. So it makes the model could be more generalizable into different interfaces. And we developed a standardized the action space that we could combine the different the data set into the same action format so that we can leverage more data, the existing data. And more crucial is the right side is we incorporate this in the monologue during the training, which can develop this sophisticated the reasoning patterns, and which through this by leveraging the knowledge or memories patterns is already memorized in the LLM. I think this is important to build more robust this action model. So in each interaction step, our agent will to generate this in the monologue the two parts, the short and the low level instructions between your visual observation and the final actions. So through this way, you could through this short and low level instruction and action, you can consider this this enables the agent can do it step by step from the different the complexity, because at the beginning you get a high level instruction and you doing this sort, like chain of thought. So you decompose the problem into some small steps, and with those steps you can to generate this low level instruction for each step about action, and then you can get a better concrete the code to ask those questions. So then it could make the model be make the agent be more robust, more accurate. So that is the motivation for it. For the training, we have a two steps. First step is the grounding, and the second step is the planning and the reasoning. And for grounding, we did some tricks, which is grounding packing strategy. What do you mean the grounding packing strategy is like we were to find all the grounding pairs, the grounding samples, which
based on the same image, and we concatenate them as a multi-turn grounding as one sample. We found that can improve the training efficiency and even to have a bit improvement on the performance. And in the second stage, it's we add this in the monologue in our training, and which make the agent could to generate this intermediate thoughts and the low-level instructions before they generate action directly. In the data part, as I said, because it's a pure vision based, we can easily to combine the different data set together and define same format for the outcome. Then we can leverage most of the existing data and create a new data set to train our model. And for the monologue, we prompt the frontier model like a GPT-4o, given this the observation image and highlight the UI element with the instruction and the final goal and the final the code, the action code, and from GPT-4o to generate in the monologue component. So this is an example. The previous is on. They have the prompts, instruction, previous action. Of course, the observation we don't add here, and this action. Then later, after this step, we will have the sort and the low-level instructions in the new data, in the new training data. So this way, we create the arc-based collection, which is combine a number of different data sets. But then finally we get for stage 1 we get the 1 million the GUI grounding data, and for stage 2 we get the 35K multi-step trajectory, which is explicit in the monologue reasoning data. It's great. And then we do the same thing like we did before. We run our model, we train our model on this agent algorithm collection data set. And we demonstrate, we showed this algorithm model perform exceptional on the grounding task. So the top is the grounding task. So there's no planner. So we can see the significant outperform the existing models on those tasks. And we also run the two-stage training. So we also have the model, single model to both grounding and planning, reasoning, action. We found that after you did the second stage training, it even improved this grounding task and achieve the state-of-art performance. And then we also did the environment, this evaluation on the offline setting on mental web. It also showed it's achieved the superior performance across different metrics on the offline setting and also on the Android setting. We also did this evaluation on the online setting, which it's a mental web and the Android world, which is this mental web live is different mental web. It provides a dynamic web-based environment to do the evaluation, and we can see the performance of the algorithm model, the superior performance, and even better than so. And there's one thing I want to emphasize is, if you see here is the algorithm 7B model with GPT-4o planner, it could be it perform the state of art in these tasks. So which means like the algorithm model have a better grounding capabilities, and this definitely can improve the final performance of this planner task, this planning task. And this is not, is also we found like they still have a big space to improve the grounding, to improve which will improve the final performance on the different computer use tasks. And we do some analysis on for different components in the algorithm on the performance. Both stage 1, stage 2 is important. In the MOOC, it's also very crucial for both the high-level reasoning and the low-level grounding tasks. And we find that in the monologue actually helps to solving the harder task, which in the right side you see one is self-plan, one is enforced plan. Enforced plan means we enforce it must generate in the monologue, and it can achieve the 20% of resolve 20% of the grounding errors. And the left side is 2 examples with and without in the model. And we also see the cross-platform benefits in the algorithm. The algorithm is trained on the web and mobile data. The OSWorld is a computer use. We found it's remarkably, although we didn't train exclusively on this computer use scenario, the model still performed pretty good, and with using algorithm 72B as the grounding plus DP4O, it's just even better than the cloud computer use model. So here I want to take here. I want to you can take away is first the algorithm model is a unified framework. It perform pretty robust across different platforms with only visual observation. And I think the visual, this pure vision paradigm, it have a big advantages on the computer use or GUI use case, which I think OpenAI already agree with this my comment, because they have the operator. And the second is, although they have a lot of progress, we still need to improve both grounding and the structural reasoning. Don't just try to improve reasoning. Actually, they have bigger the space layer you need to improve in the grounding side.